So welcome everyone to the last Flower Monthly of the year. Today is December the 3rd, and we have a super exciting two guest speakers that are going to tell us about their work in the medical domain and how they have been applying federated learning. As usual, the agenda is going to follow this structure. Now we're having the welcome message, and I will give a brief update about what we have been doing in Flower and the wider open source community working on FL for the last 30 days since the last Flower Monthly in November. And then we'll jump straight into the most exciting part of this call today, which would be two talks, one about how Flower has been used for multiple sclerosis. This will be given by Ashkan Pirmani. And then we'll get another fantastic talk by Ashkan Moradi telling us about how federated learning has been applied for prostate cancer detection. But before we get into those talks, let me give you a brief update about Flower. So you might think that because the year is ending, we have been slowing down our work in Flower Labs and also with a wider community, but you would be wrong. There are plenty of updates this time. And the first update I want to share with you is that the latest version of Flower, 1.24, it's out. It came out on Sunday, I believe, and it has some really nice improvements and extensions to the Flower CLI. So the Flower CLI is the command line tool used to execute your experiments and also monitor the execution of your runs, log into your Superlink and other Flower services. Now Flower also has support to Python 3.13. There have been a bunch of improvements in the robustness of different components in Flower, especially when you run them in a deployment setup. This is what I highlight here as the unified server app and client app heartbeat. And also we have made some quite substantial improvements to our SQLite link state. This is a database that is used by the link state when communicating and receiving updates from the different supernodes. So this is just a brief overview of the improvements that Flower 1.24 comes with. And you can find all of this and much more in the blog post that Pan, one of my colleagues, wrote. There are more updates. We have been publishing quite a few super exciting blog posts this month of November that finished very recently. Probably one of the most exciting ones was the announcement of our collaboration with Red Hat. We have been working with Red Hat for a while now to make use of their platform products to be able to run Flower federations in a super seamless way. So if you're interested on how to run Flower in your production environments using Red Hat, please take a look at the blog post that Chongsheng wrote. We got one really interesting example from Alan Yi, one of the Flower community members. He has been working for a while on quantum federated learning and decided to build a simulation on running federated learning for a quantum setup using Flower. So he describes in this blog post what are the motivations for running quantum federated learning, and he explains how he did it. Because there is an example now in Flower that Alan contributed that you can run super easily with the simulation engine if you wish to do so. I encourage everyone to do it. And more recently, you can see the date here. It was just published yesterday. This is a blog post that gives an overview on why Flower is a great choice for running industry and production-grade federated learning or federated analytics workload. So take a look at that if you are considering running your workloads in a robust production level setting. But these are not all the updates. We have been also taking part in events that finished already, like the Supercomputing conference a couple of weeks ago. You can see here we were in the booth with Red Hat. You can see Patrick, one of our great team members, and William was there as well. It was a great experience to be there and talking to other partners that trust in Red Hat to run their workloads. And more recently, actually it's happening this week in NeurIPS in San Diego and also in Mexico. Jan is going to be there, is already there, and he's going to be presenting the Flower Tune benchmark paper that we in Flower Labs and also a big chunk of the community in Flower participated in. This paper benchmarked over 25 LLMs on different domains like finance, healthcare, and general language processing. So if you are in NeurIPS, go find Jan, and he will explain you everything about the paper and what follow-up works we are planning to do on that. And final update I wanted to share is we ran a super successful hackathon in Berlin a few weeks ago. It got a lot of traction. Over 300 people registered. It was a 24-hour hackathon starting on a Friday and finishing the day after, on a Saturday, towards the end of the day. We were doing this in collaboration with Excelsius, which is another startup, super exciting startup based in Berlin. They have an incredible infrastructure or platform that allows you to submit and manage different GPUs to run your workload super efficiently. We ran towards the end of the hackathon. There were 16 demos doing all sorts of applications built on Flower and running through the Excelsius platform. Things like federated image classification, federated image classification that was supposed to run on satellites, and many other super amazing ideas. Probably you have seen many of these blog posts already announced in LinkedIn by the winners. You can see some of the winners of the hackathon here. And we were super lucky to get the sponsorship from AMD. They donated, I think it was 16 MI300 GPUs. These are almost top of the range GPUs from AMD, and all the workloads were running through them. So we are very happy that we were able to partner once more with AMD. We are planning to run many more hackathons in the next year, so please stay tuned for all the updates. And this is the last update I wanted to share, so I think now we can jump straight into the first talk. So the first talk is going to be given by Ashkan Pirmani. He is with the Leuven and also the Hasselt University. And the title of his talk is Personalized Federated Learning for Predicting Disability Progression in Multiple Sclerosis. So the floor is yours, Ashkan. Please go ahead.
Thank you very much. Let me share my screen and then we'll start the presentation. I hope you can see my screen now.
Yes, we can.
Okay, perfect. So hi everyone, good afternoon from dark and cloudy Belgium. Hope you are enjoying your time wherever you are, and thank you very much for the initial invite from Professor Lane and of course one and only Javier for an amazing Flower team for giving me this opportunity to present and share our work. As Javier mentioned, today's work is going to be about this recent paper that we published on NPJ Digital Medicine about personalized federated learning for predicting disability progression. And please feel free to consult the paper given QR code. But let me start my presentation with asking a question. Have you ever wondered how much of the healthcare data we generate is actually used to improve lives? You might say most of it. After all, this is the era of big data, LLMs, AI. We hear it every day. But the truth is shocking. 90% of the healthcare data is never analyzed. And even more shocking, a staggering 97% remains completely unused. This is why the code you see on the screen sounds so powerful. In the age of information, ignorance is a choice. Let me make it clear what I mean by unanalyzed. It means that the data just sits as it is being collected. So it's just, for example, raw patient information. Or what I mean by unused, it means that there have been some processes on data, so some insights or report has been gathered or papers being published, but they have never been applied or transferred into real practice. Let's take a step back and imagine what this means in real terms. Picture a world where most of the knowledge needed to save lives is left gathering dust. A world where the answer to some of the most critical healthcare challenges are sitting idle in disconnected databases, completely untapped. things that I'm saying is just not a fiction. This is the current reality in healthcare data. And this isn't just a missed opportunity, it's a critical failure. A failure that leaves life-saving insights locked away, out of reach for the patients who need them most. Let's come back to the MS case. Multiple sclerosis, or MS, is a chronic neurological disease affecting millions worldwide. 2.9 million is the latest update that we got. Despite its impact, MS remains a low prevalence condition. So it's not as per definition as a rare disease, but it's definitely a low prevalence disease. And the lack of cure means that the treatment is about managing symptoms and progression. So we don't have a 100% cure for people with MS. And as you can see at the bottom of the screen, this icon shows the progression of disability in people with MS. The disease can range from mild symptoms, where individuals remain fully mobile, to the severe stages requiring full-time care. This progression highlights the complexity and individual variability in MS, which demands personalized and adaptable treatment approaches. In practice, to be able to answer these kind of questions, the first step often involves accessing the data. But as this slide shows, the data is fragmented across siloed sources like hospitals, clinic, research institution. This fragmentation not only limits the scope of the research, but also create bottlenecks in accessing a full understanding of the disease. And this is particularly challenging for multiple sclerosis, where limited valuable insights are scattered across different isolated datasets. Researchers often find themselves facing a roadblock. How can we collectively learn from this data to maximize its potential and drive insights? Typically, the solution has been to pull or centralize this data into a single repository, a seemingly straightforward way to easy access and manage. While it sounds ideal in theory, but in practice introduces significant amount of challenges that complicates its effectiveness. Since we are in the Flower monthly meeting, I don't think I need to go deep into the data centralization challenges, but in my opinion, these challenges just go beyond logistics. Centralization isn't just about managing or moving data into one unit. It's about how this approach isolates and locks information into silos. It fragments the system and makes the collaboration harder and blocking the holistic view. And this brings us back to the heart of the problem. We need solutions that respect these challenges while unlocking the true potential of the healthcare data. So the question here is, how can we harness real-world data gathered in the context of care? Let me rephrase this. How can we collaborate on a global scale when data is fragmented, when data is sensitive, and when data is siloed? I think we all know the answer: federated learning. The fact that we can reach out to so many data sites and we can learn from them without moving the data from its origin, this is the key premise that we are looking for. Let me briefly also walk you through about how it works. I'm pretty sure that all of you know, but when we are talking about the federated learning, usually step 0 is having a connection between a server and client. Server you can think of as a data scientist and client as a data custodian, data provider. First step is going to executing a federated learning plan. You can think about a machine learning task. For this, a model, ML model, has to be sent to the client side, and then clients, using the model they have received from the server, they are going to train their own model using their own data on their local. And this will result to model parameter gradients. And then we will share this less informative and less sensitive information and data back to the server to be aggregated. Server is going to take this and apply some aggregation strategy. It means that we are going to end up with a global model that has been learned a bit from everyone. And we will reiterate this situation and continue it. And coming back to main study that we did, Previously within our lab, my colleagues, they had an access to one of the largest aggregated cohort of multiple sclerosis known as MS space. And using that, they did an amazing study to learn the probability of disability progression using some of the state-of-the-art machine learning models. And if I want to give you a quick overview of how the data that we had look like, we can see here that we have two columns. To just give you a brief introduction, EDSS it's a score that we usually use to quantify a disability in the people with MS, and it starts from 0, meaning healthy, all the way to the dead, 10 being a death. And these are the inclusion and exclusion criteria we had to process the data. But for example, cohort 3 EDSS means that patient at least had 3 EDSS. And that's why you see that numbers were dropping if you have to force having at least 6 EDSS. But this is a kind of typical MS cohort. I would say that the mean age is around 40 years, age at starting of the disease around 30. We have the disease duration about 10 years. And checking MS scores, MS phenotype, we see the majority, 83%, which is also true representative of the MS cohort. They are relapsing remitting, meaning that a person with MS going to have a relapse, an attack with some symptoms, may recover or may not, but they usually go back to their original state and they will have probably some relapse later on. And we see also some interesting insight about DMT, showing that disease modifying therapy, the treatment that they get, around 23%, they have none. And more than 50%, they're on low efficacy drugs. And to highlight more on the task that we had studied, the task was to predicting the disability progression using the routinely collected variables. And the progression was defined as this disability score, which is one of the well-known way of definition of the progression in MS community. If, for example, EDSS, disability score at time 2 year -1, if it's more than 0.5, and if the initial is 0, so we can think that this person had its disability progression confirmed. Otherwise, it's none. So this gives us a kind of a perfect binary classification setup that we can do our ML studies on top. Since we had this amazing benchmark study, here we try to see, okay, how federated learning would fit in this concept. And for that, we defined these 3 major objectives. The first goal that we had was to see, okay, what is the potential of federated learning for global multiple sclerosis research? Because previously, we had some federated learning on MRIs with people with MS, but we never had a study to see how it works for just routinely collected variables. So this was something that we were going to see. The second objective that we had was to, okay, what is the ideal configuration or setup that we can maximize the performance? And if there are ways to improve the performance. These were the 3 main goals that we had. And for this, we defined different analysis paradigm. The first one obviously was just the normal federated learning, meaning that server and the clients, they communicated for a couple of federation rounds and they exchanged the model. The other analysis paradigm that we had was fine-tuned federated learning, meaning that first a federated learning happened. We ended up with a globally learned model. Then we shipped back this globally learned model as a pre-trained model to the client side, and each client retrained over this globally learned model. To make it concrete, it was a full parameter-wise kind of a 2-step ad hoc fine-tuning. And obviously, we were prone to some of issues like catastrophic forgetting, but that part of the study was not explored enough. But we tried to do some to mitigate this situation with reducing the learning rate or reducing the batch size, and also try to freeze first couple of layers to see how it works. But I think this would make a really interesting next step for our future work. The third study that we had, the third analysis paradigm that we had was obviously the centralized paradigm, that we had all the data in one pool and to be able to run the full model on this and to be able to compare all these, like with the what if everyone just trains on their own locally learned model. So this kind of gave us a really nice arrays of this analysis paradigm, and we could see, okay, which works on what kind of data of which client. Since the data that we had was the aggregated data set and we have an access to the full data set, so we had to simulate it. So this data that we had, it had some natural partitioning attributes, like where the country of the origin was or which clinic it was. So the obvious scenario was to, okay, let's partition it back to its country or the clinic, and we ran the federated learning on top. But we also did some artificial or heuristic partitioning as well. For example, one of the scenarios that we tried to assess was, what if we first partition it based on country, but then we kind of do some similarity assessment, meaning that we run optimal transport dataset distance, try to see which country's dataset looks closer to the other one, and then try to make a hub. So just clustering the similar countries into one group and try to see, what if we try to reduce this dataset distance or heterogeneity. We also try to assess the kind of quantity skewed partitioning scenarios as well. To just give you a glimpse of what kind of data we had and how it looked like, we can see in the left-hand side, it's a log scale, so it's on a logarithmic scale, a bar chart, each bar representing a country, and it shows the data set size. And we see that although it's on a logarithmic scale, but still we see a really variation among the clients and their data set size. Right-hand side shows that class imbalances that we had, that blue bar represents people with MS that they didn't have the progress, so it was not confirmed. And the red one shows that it's confirmed. And we see that some countries, even they hadn't had the both label presented. So this is a really heterogeneous and imbalanced to representative scenario that we had. But one thing that really made us a bit sweat, and we went through the challenge, was how the data was partitioned. Having a look to the pie chart at the left, we see that we have these 6 big chunks, 6 slices that together they hold 82% of the data. But checking on the histogram on the right-hand side, we see that 75% of the countries, they hold less than 5K data. So at one hand, we have few giant countries with so many data, but on the other hand, we have so many countries with less data. So this is going to be something interesting to follow when we see that, okay, how federated or just the basic TED average would handle this situation. We also went through and analyzed different client ratio participation to see, okay, do we really need to have all the clients on board? Which kind of was also interesting because since we had a super imbalanced setup, presenting or not presenting of each client at some federation round, it really affected how the performance or the learning have went. And obviously we tried different federated strategies like Fed average, Fed progs, and Fed optimization algorithms. To give you more information about the pipeline that we used, obviously the data was partitioned, and then in the local, we split it to train, validation, and test set. I mentioned that we used the pre-processed data, but we did one slight change. So we applied the normalization after separating for each center to kind of avoid data leakage and preserve each center's unique data distribution rather than just normalizing all in one pool. We tried to just partition it and then normalize it based on per partition that we had. Obviously, the train model is evaluated locally, so we had a federated evaluation. Our clients, they started from the same initialization. We used neural network MLP 5-layer as the baseline model. We have Adam and Adam W, if I'm not mistaken, as the optimizer. We used binary cross entropy as a loss function with positive weights being assigned since we had this imbalanced situation. So this positive weights kind of penalize the loss function much more if it mislabels or mispredicts a positive label in our loss function. We have dropout and weight decay as a regularizer, and we had also a scheduler to kind of decay the learning rate when it plateaus to kind of give a more chance to our learning algorithm to improve it, and obviously early stopping. So I mentioned that this imbalance setup is a bit challenge for this generic federated learning, because defining a one-size-fits-all model for federated learning, it's a bit challenge, especially in a real-life scenario. Let me give you an example. I showed you we had some big clients and some small ones. So if we have chosen a large model with so many dense layers, so then we were definitely in risk of overfitting for the smaller ones. But if we have went for a small model, then we are not fully utilizing or underfitting the sheer amount of the large clients and the data that they had. So I think we had to come up with a strategic decision. Okay, who we need to care more? Are we just going to focus on the big clients and kind of discard the smaller ones, or how we are going to handle this? I assume the intuitive solution would be, okay, let each client has their own architecture, but then how we are going to aggregate or where the federation is going to happen. And the solution for that was coming with this architecture we named adaptive dual branch net. And it has this two parallel set of layers from input layers that kind of mixes the global knowledge learned from everyone, but also has some extension layers, personalization layer at the local that they're acting as a fine tuning. Let me explain more. So I said that the intuitive was to letting have them their own architecture. So we had this adaptive part for the extension layers for the countries that they had a smaller number of the data. So this extension layer could be sharing to, I don't know, one or two, or completely gone depending on the data set size. But if we have a really large country, we could get the full array of the extension layers. Obviously, these were hyperparameter tuned based on the data set size. But to answer how we are aggregating those, since we had a fixed set of core layers, then we could just aggregate this. So these core layers were acting as a globally learned pattern from everyone, picking the low-level feature and sharing back the information from the others. But the extension layers that always stays as local, they're acting as a personalization parameters. Going back to results, we see that as expected, federated learning baseline kind of trailed back centralized. But using this personalization technique, we saw that not only we can improve the federated learning performance, but we can also suppress the centralized. My intention is not to bore you down with this long table, but this is per country, and the previous one was aggregated. But if you have a look to the latest, to last row, there is this WA, which is a weighted average. I think there are also interesting insights there. As I mentioned, the fact that performance of the centralized was higher than federated was a bit expected. But one thing was not in our bingo card was that even federated perform poor compared to the local, meaning that if they have done on their own without sharing their parameters or just being pulled, they still have performed better. So this shows the importance of the personalization. Although I have to acknowledge it's a bit surreal to just compare everything with just only one metric. We have to really go down per country and compare it to see how it works. And that was kind of our goal with coming up with this recommendation metrics or model, that each country in an ideal scenario could pick its best analysis paradigm, whichever had the best performing. And the idea of our study was to, okay, give this back to the community, and they could choose what works for them the best. And if I want to summarize the hierarchy of the model effectiveness, I think that top four performers should be the personalization metrics, personalization techniques that we used. Since adaptive was just a one-step process, but for the fine-tuning, we had to do it in a two-step. That's why adaptive comes closer, but they were so close in the performance. Third one was the centralized, fourth as the local training, and the fifth one as a standard federated learning. One thing I also want to mention here, we should not also think about the performance as the key and only metric when we are talking about the federated learning. I think in my introduction slides, I mentioned the fact that we can reach out and scale up, that's the real benefit. And that should be the motive, not just only pure performance metric, because this is in a simulation setup still. So let's go back and revisit the three defined primary objectives we had for this study. The key take-home messages should be that we showed that FL is a viable option, although its performance lagged behind the centralized model. We showed that the different setup and different configuration have substantial impact on the performance. And we were able to show that with using adaptive modeling or fine-tuning, we can also fill the performance gap to the centralized model and even enhance it. I would like to thank you for your time, and I would be happy to have some questions.
Thank you, Ashkan. I think it was a very interesting talk. While I don't see questions here on Zoom, I will check the other places where we are streaming this very shortly, but I wanted to ask you first a couple of questions. So in that table where you were showing per country, what is the recommended setup for the data you have been considering? You were showing that some of them would be better off doing centralized training, but does it mean that some of the countries here, they have data came from a bunch of clinics, and what they suggested the strategy will be to centralize all that and instead of doing FL, or those countries only had one, there were no clinics inside the country, if you know what I mean.
Yeah, sure. First of all, I think that table, it's a bit unrealistic table, to be honest, because if you were able to centralize, why they need to do all this federation? So, but the idea here is to show that in what kind of scenarios, what kind of analysis paradigm works best. For example, we had some countries that they have multiple clinics, and some there were only one, so meaning that clinics, it's that country. But we hadn't had the time, but I'm more than happy to take it offline later. But if you really go through that long table per country, we see that for the federated scenarios, if countries, they have enough data, it shows that they're kind of performing par to the centralized one. But as the data goes down, I'm not sure if I could elaborate on the table. There we have some countries that they have, I don't know, 100 data points. So their performance also not that reliable metric that we can say, okay, this is the best. So that's why they can be better in the pooled performance or pooled analysis paradigm. So that was the intention of that table.
So giving a step back, so the title of your talk was to have a system by which we can monitor the progression of MS. So I don't know much about MS, but for example, just talking about the data, what are the most, if you had to pick some features that are the most indicative of degradation in the MS condition, what would be those? Is it a blood test? Is it a mobility measurement? Like, oh, you're wearing some wearables. We are measuring how much you're moving, and based on that, we know, oh, you're not moving much. Maybe you're in the later stages.
Sure.
Can you talk a bit more about this and how the data is collected in general?
This is a really interesting study, and that was completely explained the original work, which was done on a centralized base. So I recommend to go back. But we had in our study we had 42 features being included, and the idea of this study was to just lean on the routinely collected variables, meaning that we hadn't had MRIs included, or there are also some important measures that we take in the multiple sclerosis, like motor evoked potentials that shows, okay, when a brain executes a signal, how long it takes to the neurons are just delivering to the end. But we just stick to the just what whatever data being collected in the visits regularly. And the most indicative was the one that it's kind of treated as a golden standard, this disability score, which I referred as EDSS. But there are also some others like, okay, the type of the treatment that they have, because it's MS is a super complicated. Still nowadays, we don't know what it triggers it, and the fact that we still don't have a cure. So it's a bit, the whole thing is about a black box. But there are definitely some, let's say, key indicators that it can trigger to be monitored as well. I'm not sure if it was an answer to your question.
Yeah, I think it was. I think you gave some good answers, like the measure of disability. That was probably one of the answers I was looking for.
Yeah.
Okay. Very good. Just final question out of curiosity.
Sure.
How big is this data set for multiple sclerosis, or how big is the biggest data set out there? Are we
Sure.
talking about millions or
No,
just
no,
a few thousands?
definitely. That's a kind of dream scenario, but uh, this is the biggest data set in our knowledge that we were able to work on. It's aggregated of 42 countries. We are talking about the initial data that we had around 50,000 patients. But implementing this data quality and everything, we lose half of the data. So the final cohort that we were working was around 25,000.
Mm.
But then we had to apply some data augmentation, like turning these per patient to something that we refer as a per episode, that we require, okay, we need to have at least three this disability score being taken and etc. to augment the data from the original count that we had. So the final thing that we pushed to the model was around 283,000.
Okay, well, that's a big jump.
Yeah,
So sounds good. Okay, I think we are a bit over time, but thank you very much for your talk. I
with
think it was
pleasure.
super interesting, and I encourage you to continue working on this MS topic because it's really important.
Yeah,
So
of course. Thank you very much.
thank you very much. So let's jump to our second speaker. The second speaker is Ashkan Moradi. He's with the Norwegian University of Science and Technology, and the title of the talk is Federated Learning for Prostate Cancer Detection, from Simulation Studies to Deployment. So I'm looking really forward to hear what this transition from simulation to deployment looks like. So Ashkan, the floor is yours.
Yes, thank you. Let me share the screen first. Do you see the full screen?
Yes, perfect.
Yes. Okay. Hello, my name is Ashkan. I'm working at the Norwegian University of Science and Technology here in snowy Trondheim in Norway. And thank to Javier, Flower team, and Nick also to give me this opportunity to present this work here. So the work would be divided into two sections. The first part would be mostly about our radiology artificial intelligence paper that you can see on the right. And the second part is about the real world implementation of a similar scenario, which was presented at the British Machine Vision Conference last week in the UK. So you may know that prostate cancer is one of the most prevalent cancer in male population with a high mortality rate. Just to give you an impression, here in Norway, approximately 1 in every 6 men will be diagnosed with prostate cancer before the age of 80, which this is a quite high number. And at the same time, efficient management of diagnosis and treatment would have a huge impact on the individual, society, and also the economical impact of the process of diagnosing the prostate cancer. So just to give you a broad idea of how is the prostate cancer diagnostic pathway, everything would start with a blood test, and the PSA, which is the prostate-specific antigen, would be measured. And if the level is elevated, then certain threshold, the patient would be referred to a urologist. The urologist would provide some other extra tests, something like rectal examination. And then based on the decision that he would make, the patient would be referred to a radiology department, which they would take some MRI scan, and these MRIs would be analyzed by the radiologist. And if the radiologist decides that the patient needs to go further into the pathway, they would go through biopsy. But this image analysis would be really dependent on the radiologist experience. And this is the place that we enter, and we using deep learning, or more generally AI, in order to help us for these analysis purposes, because we have an aging population, and the development in the field made a lot of active surveillance programs available. And so we will end up with a lot of images that they need to be analyzed, but at the same time, the process of analysis these images is very time consuming. And we do not have enough expert personnel in order to do this. So that's why we are using deep learning in order to analyze these images. So to this end, there has been a lot of work done in the field in terms of publication or grant challenges or clinical trials in order to develop such a methods using AI to detect clinically significant prostate cancer. And one of the well-known grant challenges in this field is called PKI Grant Challenge, which there has been a lot of good developments, and they propose a lot of methods that they can even comparably to the performance of the radiologist and what is happening without AI. So this is very promising. But we all know that a deep learning based model, in order to perform really good, it needs a huge data set, which is diverse enough also to learn all the different types of scenarios happening in each field. But this data set is not typically available in one single institution. So that's the time that we need to share data with other institutes or collect data from other smaller institutes in order to make our trained model more generalizable. But this does not happen in reality, and we would face a lot of privacy constraints. So one solution here would be that we could use some sophisticated privacy-aware measures, methods like differential privacy or homomorphic encryption in order to protect the data before sharing it to some other institute. But for sure, this would be compromising the performance, the maximum utility that we can get out of this data. So here we are trying to use federated learning, which federated learning to some extent would give us some level of privacy, but we hope that it would not sacrifice the utility as much as the other sophisticated privacy preserving measures. But is that happening in this specific scenario? We are going to find out. I might not need to explain this part because I'm sure that everyone here in this meeting would know, but in federated learning, we would have a set of clients that they are connected to a server. The data set at each client would not leave the institute, and all the training would happen locally at each client. Then the client sent the trained model, which it could be the weights or gradients, to the server. Server would take care of the aggregation, send back the model to the clients, and this process would be iterated until we reach convergence. And then every client would end up with a more generalizable model trained. So just to summarize, the problem in hand here, the problem that we are trying to solve is detecting clinically significant prostate cancer based on a set of MRI images, which we call it biparametric MRI, which is a multimodality MRI. And the set of the images that we use here includes 3 modality of MRI, which is T2 weighted, ADC, and the high B value diffusion weighted MRI images. We are training a 3D unit model, which is designed based on NN units. And what we are trying to get as an output of this model is a voxel level lesion map, which basically gives us a voxel level at the same dimension of the input image, which each voxel would give us a probability of this voxel harboring a prostate cancer or not. And then this resulted output would go through some post-processing, and based on that, the meaningful lesion would be extracted and the metrics would be computed. The framework for implementing federated learning is used as a Flower. I believe this was Flower version 1. And the metrics that we are using here for evaluating our methods is based on the guidelines advised by the PKI Grand Challenge that I mentioned previously, which for the patient level evaluation, we use area under the ROC curve, and for the lesion level evaluation, we are using average precision, and the average of these two parameters would make a PKI score, which tells us that how good the model performs. In terms of the data being used here, we also use the publicly available training and development data set from the PKI Grand Challenge, which includes 1,500 cases, and these data belongs to 3 Dutch institutes. And on top of this, we are using our in-house data set as an external test set in order to further evaluate the metrics, which includes 200 cases. So the process that we did here, it was basically simulated federated learning, but we used the real world data distribution. So we had 3 clients. Each client was hosted as a separate GPU, and they were connected to a server in our local cloud, and the server was in another GPU as well. The model were trained locally, then shared to the server, and the rest of the process for federated learning. At each client, we select out 20 cases randomly in order to be used as a local test set. And the rest of the data at each client was used as a 80-20% for training and validation. And in order to have a good comparison, we trained another model called centralized here, which basically we pulled all the data from all the clients into a single location and trained the model on the entire data together. So in total, we would end up with 3 models, each from 1 client, 1 centralized model, and 1 federated baseline model, which for the local and the centralized model, we used 1,000 iteration or 1,000 local epochs, and we wanted to have the same number of iteration at the federated experiment as well. So we used 1 local epoch and 1,000 federated rounds with Fed average as the aggregation strategy. We trained this model for 5 different folds and evaluated the performances, which would come in the later slides. But at the same time, we wanted to have some fine-tuning on the configuration of the federated implementation that we had to investigate whether it would have an impact on the performance. Is this impact big or small, or how would the performance would be in general? So one of the approaches that we tried different aggregation strategies that we tried Fed average, Fed adequate, Fed Adam, and some other methods. And in terms of also finding the sweet spot or like the best combination between the local epochs and federated rounds, we fixed the number of iteration at 1,000, and then we used the different combination of the local epoch and federated rounds to find the best combination in terms of performance. So we will end up with 3 extra models as well, which one of them uses the best epoch round combination. One would use the best aggregation strategy, and the final model would use best of these 2 parameters that has been found. So we will end up with 8 different models that we want to evaluate based on the metric that we have. Here in this table, you can see the different model trained on the first column. And on the first row, you basically see the different test sets. And the numbers show the PKI score, which is the average of the patient level and lesion level metric. So D1, D2, D3 shows the local test sets. All 20s is all these 20 local test sets together combined, and the in-house is the 200 cases that we used. So we basically, as expected, we see that federated baseline outperforms the local models. It means that each client can benefit from joining the federation. And very good that federated baseline can also closely follow the performance of the centralized method. And also we can see that by fine-tuning or tuning some specific parameter that we focused on in this work, we can further improve the performance of the federated implementation that we had. So far, all good. Here, it's a further detail on the metric that we used, which was the PKI score, and it would be divided into AUC and AP. That AUC, again, is a representative of a patient-level performance, and AP is the lesion-level performance. We just wanted to have a further investigation to see that, are we improving the performance in each of these two parameters separately when we are fine-tuning the federated baseline, and the answer was yes. So again, that's good. And here in this picture, you basically see a qualitative performance of each of the trained models that we had. The local model, centralized and fine-tuned federated learning. In the first row, you see one case that all the models can basically locate the lesions without an issue. In the second case is a case that the local model would fail while the centralized and one of the clients can still locate the lesion. But we had also cases that none of the other models could locate the lesion, but the fine-tuned federated learning. I mean, at the same time, we had cases that the only model that could locate the lesion, it was centralized, but it's not shown here. So far, we had a simulated federated learning, but after this work, we thought to, what if we extend this work into a real world and implement the federated learning in real world? Would it be different or not? And we're gonna find out. So to this end, we reached out to one of our collaborators in the Netherlands, which is ZGT University Hospital. We decided to have a small experiment between Norway and Netherlands. So we set two clients, one in Norway as client one in the Netherlands as client two. And we basically focused on the publicly available data, the data that we used in the previous example. ZGT was one of the clients. We fixed ZGT as it's using its own data. And the client that we had here in Norway, we used the client number one in the previous example. And we used the data from the third client as an external test set, again, to further evaluate our model. But to implement the federated learning here in the real world, we reached out to a company called Rhino Federated Computing that I think very recently they had some collaborative work with Flower as well. But at the time that we were using Rhino, they had their implementation only based on NVIDIA Flare. So the implementation for the real world scenario that you can see on the left, it was based on Rhino and NVIDIA Flare. So Rhino would need each of the clients to have to install the hardwares locally, and then the Rhino scripts would be installed on each client separately and connects the client to the server, which for Rhino, the server was based at AWS. So when we have everything sorted out and connected, we could get access on their web-based profile to see the clients and the server and run our scripts. And at the same time, we implemented the same experiment in our local cloud in order to have a good sense of comparison between the real world and simulated version of the federated learning, meaning that we hosted each of the clients in a separate GPU and the server in the third GPU. And then for implementing the federated learning, we tested out both Flower and NVIDIA Flare in order to compare the results. So in total, for the second experiment that we had two local models, one centralized, two simulated federated learning, one of them based on Flower, which this one was the new version of Flower, and NVIDIA Flare, and real-world federated learning, which was based on Rhino Health. Here we set the number of iteration for all the experiment as 500, because in the previous experiment, we realized that we don't need to go through 1,000, and 500 should be enough until we reach convergence. And this means that for the federated scenarios, we set the number of rounds as 20 and the epochs as 25. So just to have a fair comparison, and we didn't fine tune any configuration here. So we basically used Fed averaging. Here in this figure, you see the validation score of each model performing. And on the x-axis, you see the rounds. For federated scenarios, we saved each model after each round, and then they would be evaluated on the validation data that we had. And in order to have a comparison between the local and centralized model, we also saved the model for these methods after every 25 epochs, just to be able to compare them with the same number of iteration at the federated scenarios. And based on this validation score, we picked out the best models, and we used these models in order to be evaluated on the 2 test sets that we had, which one of them was the in-house test set that we had, and the other one was the data from the 3rd client that we had from the previous experiment. So for the results on the in-house test set that we had was 200 cases. We see that, again, federated learning is very promising. It can outperform the local performances based on the PKI score. And at the same time, we do not see a big difference between using different framework in order to implement federated learning. So neither Flower or NVIDIA Flare does not really impact the performance. And at the same time, they are very closely followed by the centralized model. I mean, it might be interesting here that why one of the federated learning performs better than the centralized, but this is specified to these test sets. And it can have a lot of reason. It can have, because this is only one best model picked and evaluated. So maybe in the centralized scenario, we have better models that perform better than the federated learning models. On the second test set, we see the same trend, federated learning outperforming local models and very closely following the centralized. On top of this, we wanted to have some analysis on the time taken to execute each round of training for the real-world federated learning and the simulated one. And as you see on the left, we can see that the simulated federated learning takes less time than the real-world one as expected in order to complete a round of training. But in order to know that what exactly happens in the real world implementation, we investigated the uploading time for each of these rounds to be done, which you can see on the right. And here, it was very interesting that, I mean, again, as expected, the simulated federated learning, everything is based in the local cloud, so uploading time shouldn't take much time, which you can see. But for the real world scenario, because the data go through multiple firewalls, that's why we have a longer delay. But the interesting part here was that for client 2, which was the client based in the Netherlands, we had a longer delay than the client which was based here at NTNU. Even though the server was on AWS, we had a different timing for uploading the parameter. Yeah, this was interesting, but we suspect that this could be this could be because the university hospital in the Netherlands, they would have more strict firewalls in order to let the data or be checked in order to leave their cloud. Yeah. So here also similar to the previous experiment, we are showing some qualitative performance that, again, we see that federated learning very closely can locate the lesion same as the centralized model and outperforming the local model in most of the scenarios or most of the cases. So all in all, as a take-home messages, we realized that in a specific task of clinically significant prostate cancer detection, federated learning in both simulated and real-world experiment can outperform the local models, and they can very closely follow the centralized implementation performance. And we also realized that further fine-tuning certain parameters in the implementation can make the model more generalized on the test sets and perform better. But at the same time, we had some limitations. One of the limitations was that the hyperparameter optimization that we did here probably was not comprehensive enough to consider all the available parameters that could be fine-tuned. And also, we did not apply any privacy preserving methods on top of the weights or the gradients that we were sharing, that it could be implemented by using differential privacy or homomorphic encryption. And also the other point, it could be that in the real world experiment that we had, we only used publicly available data and we did not use the private data, because using private data would need different agreements. And in this specific process, we only had the agreements for using publicly available data. Yeah, thank you so much. I would be happy to take questions.
Thank you, Ashkan, for the super interesting presentation. I have some questions.
Yes.
I don't see some here yet, but maybe somebody ask a question in the meantime. So before that, I will ask a couple of questions. So you were presenting briefly this parametric MRI data set. You were mentioning this multimodal, but all the modalities, they are all images, right?
Yes.
So, but then each of them, do you know how each image is generated? Is using a different type of contrast for MRI, or is a different
Yes.
protocol altogether?
Yeah, the process of acquisition for these images is totally different. And each of these modalities would focus on a certain type of tissues. One of them might focus on fat, one of them might focus on water-based tissues. And so there is different types of information in each of these modalities. Because, I mean, we did not try this experiment to only use one modality and see the difference of the performance, but like with a high level of confidence, I can say that the performance would be different. There's more information in other modalities.
Something that maybe you mentioned, but maybe I missed. So you're using a unit for segmenting this 3D, region of interest of cancer.
Yeah.
Is the unit pre-trained, or you are starting from a randomly initialized unit?
Yeah, good question. I mean, first, just as a brief answer, no. The training starts from scratch, so they are not trained. But if you work with NN unit would go through the data, and based on the features of the data, it would decide some certain architecture for you, and it would say that, hey, this is the best architecture you could use. So what we used in this experiment, because we didn't want to focus on the scenario as our previous presenter, we didn't focus on the scenario that clients can have different architectures. So we wanted all clients to have the same architecture. So in the centralized experiment, which we have all the data, we used NN unit in order to decide the architecture, and then we enforced the architecture on the all clients. But the training was starting from scratch.
Okay. Do you think that, well, I'm not super familiar with the medical image segmentation literature, but I would presume there is already there are pre-trained models out there that have been trained, maybe unsupervisedly trained for image segmentation in general, and that those could be used as a good starting point and then only do federated fine-tuning, but I'm not super sure if this exists. Do you know if some works exist along these lines?
I believe this exists in the centralized manner. I'm not sure about the federated part, but in a centralized manner, we even in our group, we have some people working on a scenario that you pre-train the models on the local data set that we have. It could be a huge data set, and then you start from there and fine-tune the model on a specific set of data that you want to train your model. But I don't think if it would be very different to train it in a federated manner or in a centralized manner. Yeah.
That makes sense. Okay, cool. And then just one final question about the part of going from simulation to deployment. I think you already touched on some of the most interesting points, which is, communication costs go through the roof when you need to communicate the model to a distant location and things like that. But when it comes to making changes to the code, for example, I'm asking now in particular about the Flower implementation. Did you have to change how your client script behaves when you were doing simulation versus deployment, or Can you
Well,
talk a bit about that? Maybe it was, yeah.
Yeah, I mean, at the time that we used Rhino for implementation, they only had the implementation based on NVIDIA Flare. So if I want to compare the simulated NV Flare and the Rhino experiment, it was not much work to test out different, because the script is pretty much the same. You just tweak a little bit, and then the script would be ready to run on the simulated version. But at the same time, because I first had this script for NVIDIA Flare and then I prepared it for Flower, and in that case also it was not much work because every function, every class was already defined. So I needed to just put it in a certain structure to work for Flower as well. But it was very easy. Adaptation was very easy.
Okay, great. Great to hear. Well, I think I don't see questions here, so maybe we can wrap it up. But if anyone is out there interested on this work from Ashkan, please feel free to reach out to him directly.
Please.
So I'm gonna share my screens once more to just close today's Flower Monthly, and in fact the last Flower Monthly of the event. So we have two fantastic talks. You can reach out to them. Probably one way to find out more about both of our speakers is by checking the posts on LinkedIn we did and in other social medias about this event. Feel free to reach out to them on LinkedIn or other ways. As I mentioned, it's the last Flower Monthly of the year. So I'll see you all at the beginning of 2026. The Flower Monthly will be in January the 7th, which is the first Wednesday of the month. So take care and have a great end of the year. Okay. Thank you, everyone. Bye-bye.
Thank you. Bye.
Bye.
Thank you. Bye-bye.